So, hello everyone. First of all, I'm really glad to be here. This is my first time in Minsk, very beautiful city and beautiful people. Today, I will talk about my open source project, which is called Centrifuge. About me, my name is Aleksandr Emelin. I'm a software engineer from Moscow. I work in Avito, which is one of the biggest classified in the world. At work, we help people to sell and buy things, thus giving those things a second life, and simply let people save their money. By the way, how many Avito users here? Only a few, OK. We are popular in Russia, so maybe that's the reason. OK, so today I won't talk about things we do at work. I will talk about Centrifuge. Centrifuge is a real-time messaging server. It was originally written in Python, in Tornado framework, but then migrated to Go language. And just about a week ago, I released the new major release of Centrifuge, version 2. So all my points here will relate to this new version. Again, how many of you heard about Centrifuge before? OK, how many used in production? OK, this is just for my understanding. So it's available on GitHub. Please check it out. So what is real-time messaging? When I say real-time message, I mean message you deliver to your clients as reaction to some event happen in your application. The important property of this message is that it's delivered immediately in milliseconds after being sent by backend. This kind of messages are very useful for real-time games, dynamic counters, live chats, or simply in chat rooms. The real-time nature of such messages require it to be pushed to client from backend via persistent connection. Polling strategies when users periodically ask backend for updates are not good choice here. If we look at real-time messaging area, we actually can see lots of solutions. If you're starting to choose real-time solution for your case, you actually have lots of choices, and you have to consider several things. For example, you have to take into account, do you have existing application or you start an application from scratch? Are you ready to pay for real-time solution? What backend and front-end languages do you use? And of course, you should consider the nature of task you need to solve. Here are some links to Phil Ligetter's blog and the DeepStream Hub blogs. Both links have a nice description of real-time messaging area, possible modern real-time technologies. So if you start to choose real-time solution, you can start from there. Here on the slide, you can see only several, only the top of the iceberg in real-time solution world. There are actually more technologies. This is just some of them. Actually, if you develop your application in concurrent language, asynchronous language like Go, Node.js, or Erlang, you pretty simple. You can program without use of any frameworks or server. But you will have to solve several problems those frameworks solve for you. For example, scalability or proper connection management. Let's speak a bit about Centrifuge motivation. My personal background is Python, and to be more concrete, Django framework. How many Pythonistas here? 1, 2, 3, 4, pretty much. OK, so you know my life. OK, as you know, Django is a classic worker thread framework where each request processed by separate worker, which runs in separate process or in operating system thread. There is a limited pool of such workers, and as soon as persistent connection appears, it occupies worker forever, and we are quickly run out of available workers. This is what Centrifuge was created for. It deals with persistent connection and provides API to publish real-time messages to your clients. We can look at simplified scheme of Centrifuge integration. Here we can see three parts. Your application backend, Centrifuge, and your application users. Users connect to Centrifuge over WebSocket or suggest transports. We will speak about them a bit later. And they authenticate using connection token. In Centrifuge case, this is a JSON web token provided to clients from application backend. As soon as your application backend have something to push to clients, it uses Centrifuge API to publish message to clients. This message comes to all connected clients who are interested in event. Clients indicate their interest in event, subscribing to channels, or in other words, topics. So actually, Centrifuge is just a client-facing PubSub server. At the moment, Centrifuge has HTTP and gRPC APIs. For example, you are developing real-time comment platform, and your user just writes new comment. Comment first flows to your application backend or non-persistent connection, for example, via AJAX request in browser. You are processing that comment, validating it, saving into main application database if needed, and then publish it to Centrifuge and the message broadcasted to all interested parties. Let's go next. About features. Let's look at some features that provide Centrifuge in its design. It's language agnostic. What does it mean? It means that Centrifuge can be used in conjunction with backend or front-end written in any language. This is quite a nice thing. It's decoupled from application backend. It's a really nice thing too, because it just fits modern microservices architectures, and it provides a nice feature to gracefully degrade your service when Centrifuge, for example, is down. Your clients still can load the state from main application database, just refreshing browser page or using pull to refresh technique on mobile device. And then when Centrifuge up, they are going to receive real-time updates. Centrifuge supports GVT authentication with expiration support. It can simply integrate it with existing application. You don't need to rewrite your application code. You just need to integrate. You just need to write several lines of code to integrate with Centrifuge API. It can scale horizontally with Redis. Actually, many real-time solutions stop on implementing real-time in one process. Centrifuge goes further and provides scalability out of the box. We will talk about Redis engine, about Redis a bit soon. It has solid performance, especially compared to dynamic languages. We will talk about some optimizations later in my talk, and it has some interesting feature to recover missed messages upon client reconnects. Yeah, you are in Metro, your connection drops, then connection returns, and you can receive what you missed. It also provides information about current subscribers and channel, so you can implement something who is in that room, who is online. It works everywhere thanks to Go language. It works on Windows, macOS, Linux, everywhere. And it's just single binary, as all we know. And you can use it in your commercial and closed source apps because it's free, it has MIT license. Who's using Centrifuge? There are several companies, to name some of them. It's Mail.ru, it's internal projects of Badu, Spot.im. Spot.im actually has the biggest Centrifuge installation I've heard about. It's 300 clients online and 3 million messages per minute. Maybe there are bigger exist, I don't know. About client transport choices. WebSocket is obvious real-time transport these days because it has a big advantage. It works everywhere, in browser and on mobile devices. We know that WebSocket is a really fast protocol. It's low overhead based on TCP. WebSocket connection starts with upgrade mechanism over general HTTP, then switches to route TCP session with its own framing. It's bidirectional. This means that messages can flow from client to server and from server to client without any collisions. We remember the days when it was hard to use WebSockets in browsers. But today, the picture is much more better. According to caniuse.com, 93% of users already have browsers with WebSocket support, but there are still cases when there is no support of WebSocket on users' computer. They use old browsers, or they could install browser extension, which blocks WebSocket traffic to specific domains. To solve this, Centrifuge uses sock.js polyfill library for browser to successfully connect when there is no WebSocket support or WebSocket connection just failed. Sock.js provides several fallback HTTP transports. There are some exotic ones, but there are actually good ones like XHR streaming or event source or server-sent events. It's persistent connections based on HTTP. As they based on HTTP, this means that there is no bidirectional support out of the box, and sock.js emulates a stream of messages from client to server via separate post request to backend, or to Centrifuge in this case. One interesting thing about browsers at this moment, at these days, is that HTTP2 is growing in popularity, and there is a chance that if user opens many tabs with your applications where you establish persistent connections with backend, those connections will be multiplexed into one real TCP session by HTTP2 implementation. This is not the true for WebSockets. When you are opening new browser tab, you are open new WebSocket connection. You can solve this using local storage or shared worker to synchronize tabs, but HTTP2 just gives you out of the box this. There is an interesting specification about running WebSockets over a single stream of HTTP2 connections. It's an early stage. Here's a link to a draft. You can read. This is actually quite a nice thing we can get soon. It's already agreed by Chrome and Firefox teams. Now we looked at Centrifuge motivation, some core concepts, how Centrifuge is built inside. Let's look at more Go specifics. For WebSocket, we use Gorilla WebSocket library, obviously. There is no other choice, to be fair. Sock.js for Sock.js, we use Sock.js Go library. It's very robust, and I also tried gRPC bidirectional streaming while developing version 2 for client-to-server protocol. But after making some measurements, I realized that gRPC just does not provide any advantage over WebSocket. For example, if we land 10,000 clients on one Centrifuge node, then memory consumption on server will be 500 megabytes in WebSocket case and 2 gigabytes of RAM in case of gRPC streaming. It's 4 times difference. In terms of CPU usage, WebSocket was more performant up to 3 times under load. And if in terms of traffic, WebSocket a bit better too. So I rejected using gRPC streaming and sticked with 2 transports. About internal client-to-server protocol. First of all, it's custom, its own protocol, defined in protocol buffer schema. Here's the link. It looks similar to JSON RPC. How many of you use JSON RPC? It just feels like JSON RPC, but actually on business level, it's similar to MQTT. How many heard about MQTT? Oh, nice, nice. But there are no different quality of service levels. We will talk about message delivery models soon. There are 2 serialization formats at the moment supported. It is JSON and protobuf, protocol buffers. Developers who are using Centrifuge can choose which one he wants to use at each concrete case. It's a known fact that protocol buffers are much more performant than JSON in terms of serialization speed. Also, as protocol buffers are binary, they can serialize data into more compact format. Here we can example the same data serialized into 32 bytes in case of JSON and into just 7 bytes in case of protobuf. As I said, Centrifuge provides scalability out of the box. So user can actually connect to one Centrifuge machine, and message can be published to another Centrifuge machine, and client will receive that message. This is solved by using special entity, which is called engine in Centrifuge. Engine manages several things. It's responsible for PubSub mechanism. So clients can receive messages while connecting to different Centrifuge nodes. It manages history cache. Yeah, we have message recovery feature and messages recovered from cache. This cache has limited size and limited lifetime, configurable. And the engine manages presence information. This is information about who is online at the moment. There are currently 2 engine implementations. This is in memory engine, which keeps everything in memory, and Redis engine. It is based on, who can say on what, at which library based Redis engine? Okay, which library for Redis do you know? No one. This is Rediga. Come on. Thanks again, Gary Bird. Now let's talk about message delivery model. It is at most once. It's hard to imagine another guarantee because Centrifuge based on PubSub model and actually Redis PubSub mechanism involved. This is acceptable for many applications in the world, by the way, because the main state, kept in main application database, and Centrifuge has a role of just real-time transport. The state still can be restored by client at any moment from application database. But Centrifuge has an interesting feature to recover missed messages upon reconnects from history cache. When this feature is on, every publication has its own incremental number. Client can remember this number and recover messages from last position upon reconnect. Let's speak about optimizations we use throughout Centrifuge source code. The first one is using GoGo protobuf to work with protocol buffers. GoGo protobuf is a library that provides code uses code generation and produces highly optimized code to work with protocol buffers. Here is a benchmark. that shows that GoGo Protobuf 3 to 6 times more performance than standard Protobuf package, which uses reflection and just allocates more. Another optimization, reducing syscalls by merging messages. What does it mean? If we look at real flame graph of Centrifuge version 1, this real flame graph of production instance, we can see a lot of the widest flames relate to write system calls. You can't see, I understand, but believe me, there are write system calls in circles. What can we do? We merge several independent messages with the help of protocol design. In JSON case, we use JSON streaming to separate, to combine several messages into one batch. Messages in JSON streaming format delimited by a new line symbol. In Protobuf case, we use length prefixed format, where each individual message prefixed with variant message length. This design helps us to simply merge several independent messages, keeping them in temporary byte buffers, and then write them into connection into one write system call. Of course, we can reuse temporary byte buffers, and we do. We do this using sync pool structure. Also, we use Redis pipelining to work with Redis to achieve best performance when working with Redis. As you know, pipelining with Redis is combining several commands into one batch to send them in one request. This drastically improves working with Redis because the network involved. Let's look at what is smart batching technique on example. If you can't see what's written here, here's a link. You can look at this after my talk. Slides will be available. But the idea is simple. You have a source channel from which, okay, thank you, from which you collect items to process. And you know the fact that it's not very performant to process individual item. But you know that if you have a batch of items, you can process them more quickly, faster. So you are waiting for a first item coming from channel, and then without timeouts and blocking involved, try to collect more items from channel buffer, not much than your configured value. And then you get a batch of items and can process them. For example, make Redis pipeline and send to Redis in one write call. When we can't use pipelining with Redis, for example, when operation contains of several dependent from each other Redis commands, we use Lua scripts to do the hard work. This allows us to communicate with Redis in just one round trip in each case, and actually Lua scripts allow to make operation atomically in Redis. So we have another advantage for free. And we try to batch messages on client side in our Centrifuge clients to reduce amount of read system calls on server side. For metrics, we use Prometheus, instrumenting Centrifuge with this great library, and we periodically export stats to Graphite. So Centrifuge could fit modern monitoring stack quite well. For dependency management, we use Dep. There are no plans to move to Go mode at this moment, but maybe in future. At this time, Dep solves all our problems. For release management, I highly recommend to try Go Releaser if you have open source Go library or server, it drastically simplifies your life as developer, because as a library developer, you should provide releases to your users in a very convenient way. Docker image, homebrew formula, native Linux packages like dep or rpm. Go releaser can do this automatically, so just try it out. Let's move next. While lifetime of Centrifuge version 1, I was asked several times, is it possible to reuse Centrifuge functionality from within Go code? The answer was, yeah, you can, but on your own risk, because it was never designed for this. While developing Centrifuge version 2, I tried to segregate separate library that will be the core of Centrifuge 2 and still can be reused by core community. The result of my work is Centrifuge library. It's available on GitHub. What it provides beyond Centrifuge? It actually has almost all features I said about Centrifuge, but beyond Centrifuge, it provides support for implementing native authentication using middleware, a convenient way in Go language. It provides tight integration with backend logic, business logic. It can be very useful if you are making multiplayer dynamic browser games, for example. So you need your real-time stuff and business logic to be kept in one process. It supports bidirectional streaming. As you remember, I said that in Centrifuge case, messages flowed from client to application backend, then to Centrifuge. Now this limitation is gone. You can send asynchronous messages from client to server and vice versa. It has built-in RPC calls in protocol, so you can ask commands from your backend from client, and you have more freedom and permission management in subscriptions, for example. How it feels? I understand you don't see this. Let's zoom in the most interesting part. Here is an example. You have an API of libraries that shows how we can process some events like client connection, client disconnection, attempt to subscribe to channel, attempt to publish into channel. API is not very Go idiomatic, but it's hard to do better because there are actually lots of events you can handle. So callback style, I think, fits this better. We have several clients for Centrifuge and Centrifuge. The interesting feature is that every client works both with Centrifuge library-based server and with Centrifuge itself. The first one is Centrifuge.js for JavaScript, React Native, and Node.js. The second is Centrifuge Go, obviously for Go languages. For Go language, Centrifuge Mobile is based on Centrifuge Go and Go Mobile project and provides bindings for iOS and Android app development. And Centrifuge Dart for Dart language and Flutter ecosystem. It's a work in progress, but already works in some ways. Some examples to use Centrifuge library from client side. This is JavaScript. This is a pops-up pattern. You are creating Centrifuge object, subscribing to channel, and you have callback to manage, to process messages from this channel, and then just connect. Bidirectional messaging with Centrifuge library, where you're sending asynchronous messaging to server and reacting to asynchronous messages from server. RPC, you have a call that allows you to ask command from server via real-time transport of WebSocket, SockJS, and wait for data response to come back to you. Here are some links. The first one is the main, I think, Centrifuge documentation. It contains more information than I can tell here. Examples, some links about points I said about real-time, current situation in browsers, etc. What I can say, all my talk here is a bit more about web applications, but still Centrifuge and Centrifuge can be used inside mobile applications. I don't know many real-time examples of this in production, but there is nothing to stop someone to try. Maybe they exist. That's all. If you have questions, please ask. Thank you.
Thank you, Alex. So who has questions?
Thank you for the talk. It's a very interesting and very actual project. And maybe you have intuition or you benchmark how far it is possible to scale cluster of Centrifuge instances in terms of node count or simultaneous user count.
This is a good question. There is a problem with benchmark because I just have not infrastructure to do massive bench at the moment. So the most, as I said, the biggest deployment was on Amazon for machines. It involves 4 Centrifuge instances that handle 300,000 clients simultaneously. I think this is not a limit. I think this is not a limit, but I have no exact numbers. This setup used only one Redis instance. Redis engine supports Redis sharding, so it's not a bottleneck. You can consistently shard by channel using jump algorithm. So you can scale Redis, scale Centrifuge nodes, and there is no bottleneck in this scheme.
Anyone else? No, then thank you, Alex, very much.